So here we will start with electrolytic cells and electrolysis. As in the very first video of the chapter electrochemistry, I have discussed two types of the cell. One is electrochemical cell and another one is electrolytic cell, in which the electrochemistry works. First cell is when electrical energy gets converted into chemical energy, then the cell formed are known as electrolytic cells. Such type of cells are known as electrolytic cells. And the other type of cells are when chemical energy gets converted into electrical energy, then such type of cells formed are known as electrochemical cells, galvanic cells or volytic cells. So today we have to study about electrolytic cells. Electrolytic cells means when an external electrical energy is provided and the electrical energy will convert it into chemical energy. So such type of cells are known as electrolytic cells, and the process on which the electrolytic cell works are that process is known as electrolysis. So in an electrolytic cell, external source of voltage is used to bring about a chemical reaction. The electrochemical processes are of great importance in the laboratory and in the chemical industry. They have a very great importance in laboratory and in chemical industry. Basically, electrolytic cells are used for the metallurgy of metal. When we have to extract pure metal from impure metal, we use electrolytic process and we use electrolytic cells in this case. So here let's take an example of copper plates. Suppose we have two copper plates and the copper plates are dipped in a solution. They are present in a container and they are dipped in a solution of copper sulfate. Those copper plates are dipped in a solution of copper sulfate. Suppose one plate is this and another copper plate is this, and both the plates are connected by a battery. Both the plates are connected through a battery, and the positive end of the battery, this is the positive end of the battery and this is negative end of the battery, and we know that the flow of electron is always from negative part to the positive part. So the electron will flow from this negative part of the battery to the positive part. The electrode plate which is attached to the positive part of the battery, that will be considered as anode, and the plate of copper electrode which is connected through the negative part of the battery, that will be considered as cathode. And the electron, as the electricity will apply, then the movement of electron will take place from negative terminal of the battery to the positive terminal of the battery, like this, through the chemical reaction. So such type of process, when negative terminal of the battery gets start the flow of electron from negative terminal of the battery and then it moves to the solution, then the flow of chemical reaction takes place, then such type of process is known as electrolytic process, electrolysis, and the cell formed by such type of process is known as electrolytic cell. So similar in this case also, since at anode part we have one copper electrode, and this copper electrode, suppose it is impure copper electrode, some impurities are also present in this part. Now what will happen is some impurities is present in this part, and we put this copper electrode for purification of pure copper metal. Since anode part has impure copper plate and cathode part has pure copper plate, now what will happen, as the flow of electron starts from the negative terminal of the battery towards the positive terminal of the battery, then the solution, electrolytic solution, also have some ions. Electrolytic solution is consist of copper sulfate which have Cu positive ion and sulfate ions. copper ion and sulfate ion in the solution. So as the cathode electrode is negatively charged because it is attached to negative terminal of the battery, so the ions which are positively charged, which is present in the solution, will move towards cathode side, and the ions which are negatively charged, which are present in the solution, will move towards anode side, because anode is positively charged plate, because it is attached to the positive terminal of the battery. So as the process starts like this, as we start the current, and the movement of positive ion which is present in the solution will starts towards cathode plate, and the movement of negative ion which is present in the electrolytic solution will move towards anode side. Then what will happen, as this process occurs, then the electron which is present in the anode side will move out, will loss from the anode terminal, since we know that always oxidation takes place at anode and reduction takes place at cathode. As the oxidation takes place at anode plate, then the electron will lose and they will flow to the cathode side. They will lose and they will flow to the cathode side, and there is reduction in cathode plate, so the cathode plate will gain the electron. So as this process starts, then the impure copper metal will get reduced. The impurity from the impure copper will be desettled in the will be start settling in the solution, electrolytic solution, and the pure copper will move towards cathode terminal. So at the end, what we will get, the pure copper at the cathode terminal, and the anode plate will get thinner by removing of impurities from the anode terminal, and the copper plate will get thicker at the last. So this is the metallurgy of impure metal by using electrolytic cell or by using electrolysis. This is all about qualitative aspect of electrolytic process, and with the help of this qualitative aspect, many metals like sodium, magnesium, aluminium are also produced by large scale by electrochemical reduction of their respective cations. Similarly, if we come towards quantitative aspects of electrolysis, then the quantitative aspect of electrolysis was produced by the scientist Michel Faraday. He gave two laws on the base for the quantitative aspect of electrolysis. First law is Faraday's first law of electrolysis. Second law is known as Faraday's second law of electrolysis. So according to first law of Faraday's first law of electrolysis, the amount of chemical reaction which occur at many electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. So according to first law of Faraday, the amount of chemical reaction, because we are talking about quantitative aspect, so here we will discuss the amount. So the amount of chemical reaction which occur at electrode, which is occurs at electrode during electrolysis, the current for that time, the current is proportional to the quantity of electricity passed. It means the amount of electrolyte, suppose the amount of electrolyte is M, that will be directly proportional to the quantity of electricity passed this charge. The flow of charge, that will be directly proportional to the flow of charge. So the amount of electrolyte is directly proportional to charge Q. Now on replacing this proportionality sign, M will be equal to ZQ, where Z is known as electrochemical equivalence. Since M is equal to ZQ and this Z is a constant, this is known as electrochemical equivalence. Since we know that Q is the charge which is equal to the flow of current into time, since Q is equal to IT, so from here M, on replacing the value of Q in equation of M will be equal to ZIT, where Z is a constant and Z is known as electrochemical equivalence. Now the definition of electrochemical equivalence. What is electrochemical equivalence? Since suppose the current passing in the solution is 1 ampere and it passes at the time of 1 second, then the value of Z, then Z will be equal to M. It is equal to M, it is equal to the mass. Electrochemical equivalence becomes equal to mass as I equal to 1 and T equal to 1. So from here the definition of electrochemical equivalent of a substance may be defined as the mass of the substance, that is this is equal to M. It is the mass of the substance deposited when the current of 1 ampere is passed for 1 second. That is the quantity of electricity through the 1 coulomb is passed. So this is all about the first law of Faraday, which tells about the quantitative aspect of electrolysis. Now come to the second law of Faraday. Second law of Faraday states that the amounts of different substances liberated by the same quantity of electricity passing through that different electrolytic solution. Suppose we have two different electrolytic solutions are present. And these two electrolytic solutions are connected through the same electrical terminal. Then at that time, the amount of the different substances liberated or at the cathode side, then that will be considered by the second law of Faraday. If we are talking about two different electrolytes which are connected through the same terminal of the electricity, then what will happen? The amounts of the different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. They are proportional to their chemical equivalent weights. Equivalent weights, meaning of equivalent weight is atomic mass of the metal divided by number of electrons required to reduce the cation. It is the atomic mass of the metal divided by number of electrons required to reduce the cation. And number of electrons required to reduce the cation means the nature of cation. Either it is monovalent, divalent, trivalent, the nature of cation. Suppose we have NaCl, we have copper. Cation of copper is Cu plus 2. Cation of copper is Cu plus 2. It is a divalent cation. So it means this line means the number of electron required to reduce the cation means it needs 2 electron to get reduced to form Cu ion, Cu metal. Since we know that the copper, for copper the cation is Cu2 positive. Cu2 positive is stable for copper. For copper metal, its cation is Cu2 positive. So the number of electrons required to reduce the cations for copper 2 positive are 2 electron. After gaining of 2 electron, it will get reduced and it forms copper in its pure form, copper in its metal form. So the number of electrons required to reduce the cation for copper 2 positive is 2 electron. So this is the meaning of this line, that if it depends on the number of electrons which is required to reduce a particular metal cation. So now from the second law of Faraday, we can conclude the amount of current. We can use the amount of current which on passing to the different two electrolytes, that how much amount of current is required to reduce the particular metal. In case of copper, the amount of current will be, since there are 2 electrons which are needed, to reduce this copper, so the amount of current will be twice. Similarly, for sodium is present in Na positive form, only 1 electron is required to reduce sodium ion, so the amount of current in case of sodium is 1 time. For aluminium, it is ion of aluminium is Al3 positive, so the electron required to reduce aluminium is 3 electron. For this, the amount of current for aluminium will be thrice. So from here we can calculate the value of amount of current from the second law of thermodynamics. Second law of Faraday. From here, initially there is no constant source of current, so the Faraday used for its practice, Faraday put a quantity that for measuring the quantity that is known as coulometer. But now we have the constant source of current. Now we use, for measuring the quantity of current, we use the equation Q equal to IT, where Q is in coulomb and I is in ampere and T is in second, because T is time here. The amount of electricity required for oxidation or reduction depends on the stoichiometry of the electrode reaction, as we have discussed earlier. Since we have the reaction of silver positive ion plus electron, it get reduced on silver ion, which is of positive charge, it is getting reduced by gaining of one electron, and it is reduced in the form of silver, pure silver. So 1 mole of the electron is required for the reduction of 1 mole of the silver ion. Here it is 1 mole of silver ion and 1 mole of electron is required for the reduction of silver ion. From here we know that the charge on one electron is equal to 1.6021 into 10 to the power minus 19 coulomb. For one electron the charge is 1.6021 into 10 to the power minus 19 coulomb. Therefore the charge on 1 mole of the electron will be equal to, we will multiply the charge of electron by 1 mole, and the number of ion in 1 mole is 6.023 into 10 to the power 23 mole multiplied by the charge of the electron, 1 electron. So we will get the charge as charge for 1 mole of the electron, we will get as C equal to 96487 coulomb per mole. And this quantity of electricity is called Faraday. This is called 1 Faraday. It is represented by F. We have already discussed it. For approximate calculation, we use 1 Faraday equal to 96500 coulomb per mole inverse. So, for 1 mole of electron, the charge is 96500 coulomb per mole inverse. Now let's see for the electrode reactions of magnesium ion. Magnesium ion, on getting 2 electron, it will get reduced to magnesium. Similarly, aluminium 3 positive ion, when it will get 3 electron, then it will reduce to aluminium. It is obvious that 1 mole of magnesium ion and aluminium ion require 2 mole of the electrons, 2F for magnesium, and 3 mole of electron for aluminium, that is 3F. The charge passed through the electrolytic cell during electrolysis is equal to the product of ampere and the time in seconds. From here we can easily calculate the value of charge which will be passed, since charge is equal to I into T. From here we can easily calculate the value of charge Q. Now in commercial production of metal, current as high as 50,000 amperes are used that amount to about 0.18 Faraday per second. Now come to the question. Here is the question that a solution of copper sulfate is electrolyzed by 10 minutes. We have a solution of copper sulfate which is electrolyzed by 10 minutes with a current of 1.5 ampere. Now what is the mass of the copper deposited at cathode? We have to calculate the mass here, calculate the value of M of copper which is deposited at cathode. Given is time is given, that is 600 second. Charge is given, we know the value of charge. Charge is current into time, I into T. Current is 1.5 ampere and time is 600 seconds. Since 10 minutes is given, that is 600 seconds. That will be equal to, the charge will be equal to 900 coulomb. From here the charge comes as 900 coulomb. Now according to the equation, we know that copper on gaining of 2 electron, it will get reduced to copper. Copper ion gains 2 electron, it will get reduced to copper. So we require 2F of the charge, 2 Faraday of the charge, since 2 electrons are needed. So we require 2 Faraday of the charge to deposit 1 mole of copper. Because we know that 1 Faraday charge is for 1 mole of the electron. So for 2 mole of the electron, 2 Faraday charges will be produced. So on producing 2 Faraday charge, we know that 1 mole of 2 Faraday charge is deposited to 1 mole of the copper, because 1 mole of the copper is forming at cathode. For 900 coulomb, the mass of copper deposited will be equal to 63 gram per mole, which is the mass of 1 mole of copper, into 900 divided by 2 Faraday charge. So the value from here, the mass of the copper which will be deposited at cathode will be equal to 0.293